Welcome back to another session of High School Geometry with Netz and Weichel. This is Mrs. Netz,
And this is Mrs. Weichel.
and we're going to go ahead and get started with 1.5 surface area from a net. Our learning target for the day is by the end of this lesson, you will be able to calculate the surface area of a three-dimensional figure. There are many objects that have complex shapes to increase their surface area inside of your lungs, intestines, and brain, air cleaners, radiators. All of these or others that avoid flat shapes to minimize their surface area is pine needles, cactuses, and things like that. They have minimal surface area, so that way they don't dry out. Other surface area things are things like the outside of a box. How you will know you mastered it is when you can calculate the surface area of three-dimensional figures.
All right, let's go ahead and get started. In order to work with surface area using a net, you need to know some basic area formulas. So the shapes that I have on the screen right now are going to go on your guided notes under area formulas. You should be able to actually do this without watching this lesson because you've been working with rectangles, triangles, and circles for a few years now. But we're going to go ahead and just remind you how to work with them. So a rectangle is going to be a quadrilateral that has two same sides here and two same sides over here, and then right angles in the corners. Down here we're going to call this our length, and we're going to call this our width. And to find the area of this rectangle, you simply multiply the two dimensions together, length times width.
And with this, it doesn't matter which side you call the length and which side you call the width. Because you are multiplying, an order doesn't matter when you're multiplying.
Due to the commutative property.
It doesn't really matter which one you call which.
For a triangle is actually half of a quadrilateral, so it is going to be, for the most part, the same exact formula. You do need to have, we're going to use the words base and height for a triangle. The base is usually going to be the bottom of the triangle. And then your height has to be perpendicular to the base that you are using. So for the triangle on the bottom, well, I've given you a right triangle, so this would be our height because the base and height are perpendicular to each other, making that right angle. In the top triangle, that one, these corners are not right angles, so our height is actually going to be located on the interior of the triangle right here. That would be our height.
So just remember, height is always straight up and down.
And then to do this, you're going to do, again, the same thing we did with a rectangle, but it's half, so you're going to be dividing it by 2. So you'll see it written the way, I know Ms. Netz writes it this way, I usually write it as half times the base times height. Both will produce the same result for area. And then the last shape on my screen right now is a circle. To find the area of a circle, you need to know the length of the radius, and a radius is going to be from the center to the circle, or half the diameter. And to find the area, you are going to take what pi is and multiply it times the radius squared. For what we're going to be doing today, you won't need this for any other shape, but we are also going to be using the circumference of a circle, so I just want to talk about that formula. If you're using the radius, remember circumference is the same as like the perimeter of the circle. It's the distance around the circle, the entire circle. To do that, you are going to take the radius doubled, or the diameter, and multiply it by pi. So you'll see that written either way, pi times diameter or 2 times pi times radius. The next thing we're going to look at is just other polygons. So something to keep in mind is that all polygons can be broken into triangles. So you guys have quite a bit of space still on this front side of notes that you can add in your own notes. So I would just draw some other polygons. We learned about a bunch of polygons in the previous lesson in 1.4. You can say here I have a triangle broken up into triangles. Here I have a quadrilateral that is broken up into a bunch of triangles. A pentagon broken up into a bunch of triangles. And then right here a hexagon broken up into a bunch of triangles. So I'm not going to give you another formula for other polygons because you're just going to take any other shape that is not one of these and you're just going to make it into a triangle, a bunch of triangles, and you're going to find the area of those triangles, which is what I just went over here on the previous screen.
To make a triangle inside of another polygon, all you have to do is pick one of the vertices and then draw a line from that vertice to either a center point or one of the other vertices. If you're drawing from a vertice to another vertice, you'll notice that that won't work on the triangle because you'll just be redrawing the triangle if you were to do that. So we use a middle point. If you're doing anything like a square or a pentagon or a hexagon, you can go from vertice
An
to
even number of
vertice.
sides, you could go vertice to vertice.
Yeah.
Odd number, you'd have to go to the center.
Yeah, so just keep that in mind. But any of your polygons you can absolutely turn into various numbers of triangles.
So I went ahead and we're going to look at regular polygons only. I won't give you any irregular ones in this lesson. We're going to find the area of this hexagon, this regular hexagon. To do this, you're simply going to create triangles, and because this is an even number of sides, it's a little easier to draw. So we're just going to basically connect opposite vertices, and what ends up happening is you make 6 triangles that are exactly the same. So what I can now do, I can find the area of one of them. You'll know the side length, that would be the base, and you'll be given also the height. You'll get that number. You'll get both those numbers from us. And you can simply work it out. So base times the height divided by 2, or half base times height. And then you're going to multiply that, because that's only this one triangle. You're going to multiply it by how many triangles there actually are, because they're all the same. A hexagon created 6 congruent triangles. So basically the number of sides is going to be the number of triangles you're creating. So you will always multiply this by the number of sides. So please make sure you have this on your notes. Whoops, number of sides.
Perfect.
Okay, 2 more things we're going to have you write on this side. Just what is a net? A net.
Well, think about it. Like if you're wearing a hairnet, it's something that wraps around my hair.
A 3-dimensional figure. So a net is basically when you take a 3-dimensional figure and flatten it out. I always picture moving boxes. When you buy a moving box, usually you see a flat box that you have to pop open. It's starting out as a net, and then you pop it into the 3-dimensional shape. So it's actually working the opposite direction of my diagram I have on the board. So just know that a net is going to be a flattened out 3-dimensional figure. So please make sure you know that, write that down. This is another vocabulary word for chapter 1. And then the last vocabulary word that we're going to go over today is surface area. What is surface area? Surface area is going to be the area of each side, each shape that you're seeing in the net, and then you have to add them all together. So remember, a net is a flattened out 3-dimensional shape. So if you were to pop it back to its 3-dimensional form, you would be finding the area of all the sides together. So you would simply add all those sides together.
Perfect.
So go ahead and turn your notes over. We have 4 nets given on the back side. You guys have a table that you need to fill out. We're going to do some of it together, and some of it we're going to ask you to pause this and work it out on your own. So the first one, we actually have this would be a rectangular prism, or like a box if you were to fold this back up into a 3-dimensional figure. So the shapes and quantity. If you're looking at this, there are 6 shapes, and they're all not the same size, but they are all the same shape. What are we seeing? We're seeing 6 rectangles. So we're going to go ahead and say that they're all 6 rectangles, and I went ahead and also put the dimensions of each one. You don't have a lot of room to do that, so you may not want to do that.
Well, you could do that on the actual picture, and we'd actually like for you to do that on the actual picture.
And here's where we would like to see color.
So you have to use kind of hints from we've only got 2 measurements, but we have so many lines that we need to know, or sorry, 3 measurements. We have so many lines that we have to have numbers on, and we only have numbers on 3 of them.
So you kind of have to predict what is going to be the same. When you think of a box, the top and the bottom are going to be the same. The front and the back are going to be the same, and the left and right are going to be the same. So if we were to fold this up, this would be like the bottom, and then this would be maybe the front and the back, and then this would fold up to be the top. So you know these two are going to be the same. If this folds up and this folds up, these two would end up being the same.
So Mrs. Weichel, because I'm taking one measurement and applying it to a bunch of other measurements, do you think that'd be inductive or deductive reasoning?
What do you think?
Because I'm taking one thing and I'm applying it to a bunch
multiple.
of other things.
So this would lean more towards inductive reasoning.
Very cool. Huh, another vocabulary word.
So what we're going to ask you to do now is pause the video. So you have 6 rectangles in your shapes and quantities box. In the area of each shape, you are actually going to be working out the area for all the shapes. The blue ones that I have here, we know that this is 4 by 5. We know that this one up here is the same, so it's also 4 by 5.
Now the reason we know it's the same is because you have to somewhat imagine this box being folded back up. And if one side of the box is going to be 4 tall, then the other side would be 4 tall as well. If it's 5 wide, then the other side would have to be 5 wide as well. So now we're going to have to take those measurements and
Now-
apply them to the sides that go around the box.
So if the top is 5, then the bottom must also be 5, and there's a dimension for, whoops, wrong color, would be the dimension for the side of the rectangle. Going this way, we know it's going 7. Well, all of these are going to then be 7 because of what this is folding back up to. So now I know that this pink rectangle is a 5 by 7 rectangle. And then again, I talked about this at the beginning. If this were the bottom, this would end up being the top if it were to completely fold up. So I know this one would also be a 5 by 7 rectangle. Lastly, these green ones, if this were to stand up, we talked about how it's 4 tall. Well, they all would be 4 tall. This would be standing, like these would match up if we folded this back up like a puzzle. So this would have to be a 4. And then again, this way we're going 7 all the way across. Right here, this would be 4, which means this would be 4. And this one would match up with this one if we folded them up, standing straight up and down. So we know this would be a 4 by 7 rectangle as well.
So what we would like you to do is pause the video and then find the area of these 6 shapes. Write them down, and then in the far right column, write your total area. Go ahead and pause.
Okay, so this is what I should see on all of your papers.
It's like magic. It just poof.
Poof, there it is. The 2 pink rectangles should have had an area of 35 units squared. The 2 green, 28 units squared, and the 2 blue, 20 units squared. And when you add up those 6 rectangles, you get a total surface area of 166 units squared.
Now, because they didn't tell us inches, feet, centimeters, whatever it was, you're always going to then say units. And because we are talking area, it is important that you always say squared. So let's go on. Let's do another shape.
Now we're going to look at this. If this were to fold up, it would be a cylinder. So we're looking at the shapes and quantity. There are actually 3 different shapes, but 2 of them are the same. So what do you see 2 of?
Circles.
And then 1
rectangle.
There you go. 2 circles, 1 rectangle. So when we go into the next box for area of each shape, you're going to be finding the area of the 2 circles and the area of the 1 rectangle. So we talked about how you're going to find the area of the 2 circles. I'm giving you a radius of 6. For the rectangle, we did not give you all the dimensions that I needed to. So let's go ahead and talk about what we are going to use for the dimensions. One of them we can see is 15, but we don't have what this side is going to be.
So we kind of have to think about this. If we were to fold this net back up and look at where that rectangle wraps around, it wraps around the outside of the can. The outside of the can would then be your circumference.
which is why we talked about that on the other side. If we were to wrap, if this circle stood straight up off your paper and this circle stood up straight off your paper, this would end up wrapping right around it. I like to use paper towel rolls in my class when I talk about this. The paper towel is wrapping around that cardboard
Tube.
Thank you. I couldn't think of the word. So we need to find the circumference of this circle. That's going to be the length of our rectangle.
So anytime you are finding the surface area for a cylinder, what you need to remember is for the rectangle, it's always going to be the height of the can, I guess, and then the width would be the circumference of one of your circles.
So the length or width will be 2 pi r every time when you're working with surface area of a cylinder.
Or pi d.
Or pi times diameter. So in this case, if our radius is 6, our diameter must be 12. So the circumference would be 12 times pi. Moving forward, whenever working with pi, we would like you to leave it in terms of pi unless we ask you otherwise. So for this, for right now, go ahead and leave the pi sign. Treat it as if you would treat a variable.
When doing your assignments on Khan, if they ever ask you to leave your solution exact, they're asking you to leave it in terms of pi. Because pi is an irrational number that goes on forever, it is impossible for us to give an answer in an exact number. So we approximate or we round.
So we're going to go ahead and ask you guys to again pause the video please and go ahead and figure out the exact area of the two circles and rectangle and then add them together to get your exact surface area. Okay, so here it is, poof.
This is what you should have gotten.
You should have gotten 6 squared pi is 36 pi for both circles. And then 12 times 15 is 180, so the rectangle is 180 pi. When you add 36 plus 180, you get 252 pi units squared for the exact answer. Now go ahead and type 252 times the pi sign on your calculator, and that will give you the approximate answer of 791.68 units squared.
Please do not use 3.14. Use the pi symbol on your calculator so that way your approximation matches our approximation. So let's go on to our next shape.
So this one we're just going to help you just very slightly. Again, with the shapes and quantity, it should be very easy for you to see what you have. We have 2 triangles, 2 right triangles, and 3 rectangles.
The only trick here on this problem is that we are missing one of the sides of the triangle, and you would think that we just simply don't know that information. But you know that using Pythagorean theorem that you got a little bit of in Algebra 1 and also in 8th grade math, that a squared plus b squared is equal to c squared. So for that one, to find out your third leg, you would do 5 squared plus 12 squared is equal to c squared.
And the reason you're going to need to do this is not necessarily to find the area of the triangle, but you're going to need that for this rectangle. So we have 25 plus 144, which is 169, and then the square root of 169 is
13.
So we know that this side is 13. And again, picture if we were to wrap this back up. If this triangle stood straight up and this rectangle stood straight up, I would know this is also 5. Front to back here is 8, so this must be 8. So now you have the dimensions of that rectangle. The blue one, you know this way is 12, this way must also be 8, so you have the dimensions of this rectangle. And then lastly, the reason we needed that 13, if this triangle is standing up, this one is going to be wrapping kind of at a diagonal back around, giving this length as 13, and now you can find the area of this rectangle. So go ahead and pause the video and find the area of each of those 5 shapes and add them all together. Okay, here it is. You should have gotten an area for each one of 30 for triangles, then 40, 96, and 104 for the 3 rectangles, giving you a total surface area of 300 units squared.
Awesome. Let's try a harder one.
So now what you have is a pentagon.
Now, we had told you that you could take any shape whatsoever and divide it into triangles. So you could take this pentagon and divide it up into triangles by simply drawing a line that goes from the center to the outside. You know the area for triangles. I would like to see what they can do with this one.
Okay, so go ahead and find, basically you're going to do 10 triangles and then add them all up.
Good luck.
Okay, so you should have found the area of this triangle with a base of 2 and a height of 5.2. That gave me an area of 5.2 once you found it, and there are 5 of them. Then the pentagon, you found the area of one of the triangles, which is 2 times 1.6 divided by 2, and then times 5, which gave me 8. You had to then add the 5.2 5 times, and add 8 to that, giving you a total surface area of 34 units squared.
If this is something that you're struggling with, you're going to need to go ahead and talk to one of your teachers, especially with drawing the triangles inside the different polygons.
So, as she just said, if you need to message us on Remind, please do so, or email us, or contact your own personal teacher.
So, hey, Michael.
Hey, what?
What do you call a tree if all the leaves are shaped like polygons?
What?
Geometry.
All right, thank you for joining us, and we will see you in chapter 2.